For a long time, people all over the world thought that God created the universe. In 1931, the Catholic priest and physicist Georges Lemaitre suggested an idea. The universe started with an explosion of a microregion billions of years ago. This became known as the Big Bang Theory. It became accepted by the cosmology community, who wrapped Lemaitre's theory in complicated maths. Lemaitre said he had built his model on thermodynamic considerations. He meant the second law of thermodynamics, which states that energy tends to spread out evenly over time. This implies that all sources of concentrated energy will eventually run out, causing a heat death of the universe, where all the stars will stop burning, and the universe will become much less dynamic. Over the 20th century, this theory was moulded and remoulded to fit the incoming telescope data. By the end of the 20th century, the Big Bang model and its supporting theories suggested that over 95% of the mass of the universe was invisible to all known methods of direct detection, and that it's not made of anything we've ever found. Further, most of this mass was in the form of an unknown energy that is able to repel and propel the large components of the universe away from each other. While establishment cosmologists are happy to keep the Big Bang model as their preferred model, many consider these glaring features of the Big Bang model to be massive indications that the theory is wrong. I think the Big Bang model is wrong. Completely wrong. When you research it, you find a long history of flaws and failed predictions of the Big Bang model. When a theory's predictions fail to match observations, the theory is supposed to be falsified. Yet cosmologists have clung to the Big Bang theory. The Big Bang model is supposed to be a paradigm shift to replace old religious theories of creation with rational, scientifically deduced principles. Yet it still required God. Children who read about the Big Bang will immediately think, if the Big Bang made the universe, what made the Big Bang? Those who support the Big Bang model will insist that the Big Bang doesn't require God, and that the Big Bang came about due to physics and conditions that we're not sure about yet. These people have been tricked by incomprehensible maths and the prestige that cosmologists hold for themselves, meaning, if you don't understand that the Big Bang is true, it's because you aren't clever enough. The truth is, it's impossible to guess with any confidence what came before the Big Bang. Science is based on what is happening now and nearby, and trying to predict when it will happen again in the future. Suggesting there was a unique special event 14 billion years ago is a notion that is as far removed from the realm of science as possible. It's just a mythical story. Lemaitre might have had sincere intentions of trying to shift the theory of creation from religious to scientific principles, but we must consider that he was a priest who had been immersed in religious ideas for a large part of his life. His stated main consideration in revising the theory of creation was to accommodate the second law of thermodynamics. That could be considered an improvement, but since then observations have shown the Big Bang model does not describe the universe.
I don't believe in the Big Bang because there has been a theory rather well worked out of how the Big Bang is supposed to have happened. And it seems to me that it is not likely to be correct. So there are too many too many assumptions in it for me to like it, and it is too far removed from astronomical observation. Quite obviously, we can't observe what happened 10,000 million years ago, whereas we can observe what happens in the center of a galaxy today. And so I prefer always to choose the alternative that allows one to carry out observations now. I don't like the idea that something is dependent on a cause that I can never verify. So I don't like this because it's in the past. It's all over and done with. I can't get at it, as it were.
How do we get a scientific theory of creation? A requirement of science is that the subject being considered can happen now and in the future. So one-off events in the distant past don't qualify as scientific. Also, let's note that the universe is currently broken up into components, such as galaxies, star clusters, stars and planets. If creation can happen now, it seems unlikely it requires all the mass in the universe to collude all together. The Big Bang got that bit wrong too. Therefore, let's make the sensible assumption that creation doesn't need all the universe to be in the right place and time. Instead, let's assume that only a small fraction of the universe at any time is needed for creation. This is a basis for what some would call a steady-state theory of creation. A steady-state theory of creation is inherently scientific. This is likely part of the reason why many great thinkers have preferred steady state. Men such as Fred Hoyle, Thomas Gold, Herman Bondi, Geoffrey Burbidge, and Giant Narliker. A one-off event in the distant past is inherently dependent on divine intervention. Anyone wanting to apply science to deduce the theory of creation must on principle reject the Big Bang in favour of any steady-state theory. In 1927, Werner Heisenberg asserted that the exact state of any physical system could not be known with absolute accuracy. He got this result by modelling matter as waves using Fourier analysis. But we don't need to be good at maths to appreciate why Heisenberg's theory fit in with the physics of subatomics. At first, physicists thought that Heisenberg's results was a reflection of the inherent impracticality of trying to measure very small fast things with high accuracy. When measuring things at the subatomic scale, there's no rulers or stopwatches, only point-like objects. It becomes akin to a game of bowls or snooker in the dark. A ball is thrown in the direction where you think another ball is, then you look for signs of collision. You set up a net to catch your thrown ball. If it's caught not where you expected, then that's a good sign it hit something along the way. But you're not quite sure when or where it hit the other thing. This principle of not being sure of the state of a physical system became known as the uncertainty principle. So physicists first thought it was a statement about a principal inherent shortfall of any method to measure a system. But that wasn't the truth of the uncertainty principle. In time, it was realized that systems actually don't have precise values of velocity and position and energy. No matter how accurately they are measured, their values cannot be found exactly, because objects don't have exact velocity and position. The uncertainty principle has been found to be true for all systems ever tested. What about a system with no energy or mass? Only empty space, also known as a vacuum, has zero energy and mass in classical physics. But the uncertainty principle forbids any system to have exact energy. Therefore, empty space cannot have exactly zero energy. If so, this would agree with the third law of thermodynamics, which states no system can reach absolute zero temperature. As the 20th century wore on, different experiments accumulated over the years were all suggesting the vacuum did indeed have an inherent energy above absolute zero that could not be removed. But in what form was this vacuum energy? There doesn't appear to be any mass in a vacuum. By the 1970s, vacuum energy was being described as a universal field of fluctuations, a spontaneous creation and rapid annihilation of virtual particle pairs. These virtual particle pairs, typically thought of as an electron and positron, are created out of nothing, exist for a very short time, then annihilate each other and disappear out of existence. Unlike real particle pairs, when a virtual pair annihilate, there is no release of photons. During their brief existence, virtual particle pairs can interact slightly with the universe, a small nudge here and there at the subatomic scale to subatomic particles. Although under special conditions, virtual particle pairs can have effects at larger scales. So one of the striking outcomes of 20th century theory was that all of space in the universe, both empty and non-empty, contains this background vacuum fluctuation energy in the form of virtual particle pairs, spontaneously being created, existing for a very short time, then annihilating each other. Vacuum energy is also called zero-point energy. One of the most striking things about zero-point energy is it's not bound by energy conservation laws. The reserve of zero-point energy is neither depleted nor replenished by interactions with the universe. It has, in a way, an infinite reserve of energy. This has led to some speculation about a machine that could endlessly extract useful energy from the vacuum. But zero-point energy is both very weak and evenly spread out. Zero-point energy extraction machines fail in the same way perpetual motion machines of the second kind fail. For energy to be useful, it must be concentrated or denser compared to some other reservoir of energy. Zero-point energy is not concentrated compared to any other energy reserve. But is there another way to extract energy from the vacuum? In 1931, Fritz Sauter derived a strength for an electric field, which if applied to a vacuum, would cause the zero-point energy virtual particle pairs to become real. How can an electric field do this? All that happens in the case of a strong electric field is the mutual attraction of the virtual pair is overcome by the external field, and the particle pairs are separated. So instead of mutual annihilation, the pair travel their separate ways as new real particles in the universe. This is the idea of a quantum critical field. The physics community accepted quantum critical fields as theoretically correct. For decades, scientists have been wondering about creating a quantum critical field using high-power lasers. A laser is an electromagnetic wave composed of an electric and magnetic field. To get a strong electric field, all that needs doing is just make an extremely powerful laser. Throughout the 20th century, the strongest lasers were nowhere near powerful enough to reach the Sauter limit. Even today, the most powerful lasers are a long way short of creating an exavolt electric field. One of the most powerful lasers planned in the next few years will be housed in the ELI Research Centre, currently under construction in Romania. The ELI laser is planned to have an electric field on the order of 1 petavolt per metre. That's around 1,000th of the electric field of a quantum critical field. However, the rate at which lasers continue to improve gives hope that a quantum critical laser will be manufactured within the next 30 years. While there has been a modest and steady interest in the physics community for quantum critical fields, a variation of the idea became world famous amongst cosmologists and popular science readers, and it's worth having a look at.